We're going to look at the next design paradigm or design technique today, which is dynamic programming. So unlike divide and conquer, which does not have a specific category of problems which it is used for, dynamic programming has a specific category or a type of problems called optimization problems, and it is generally used only to solve optimization problems with overlapping subproblems. So I will explain both these terms now. I want to clarify what an optimization problem is, because I encountered a few people who have a little confusion in that concept. So if I give you an array with integers and ask you to find the maximum element or a minimum element, that is a search problem. That is not an optimization problem, because the quantities there are fixed. You are just searching through them and finding something. So I can replace the find max question with find second max, or find min with find second min. The nature of the problem is the same. So that does not qualify as an optimization problem. That is a search problem. Whereas if there is a specific quantity which can take multiple values, and when it takes a certain value, it happens to be at its peak or at its lowest, and you have to find that peak value or that lowest value, that is an optimization problem. So for example, you might have come across this in your 12th standard math. There's something called linear programming problems. So a factory makes tables and chairs. They have space to store like at most 60 units of furniture. One table costs this much, one chair costs this much. They can spend at most 500 rupees. The selling price of one table is this and one chair is this. So find the number of tables and the number of chairs they make, so that their profit is maximum or their expenditure is minimum. So there, the profit or the expenditure, it can take different values depending upon how many chairs and how many tables they make. So from those different values of chairs and tables, you choose one particular configuration where the profit is minimized or the profit is maximized or the expenditure is minimized. That sort of problem is called an optimization problem. So dynamic programming is used for problems where you have to maximize or minimize a quantity, and when these problems have overlapping subproblems. This again is in direct contrast to what we learned in divide and conquer. Here the subproblems have to be dependent on each other. You cannot solve a problem of size n without referring to some information provided by the same problem of size n-1, n-2 and so on. So for overlapping subproblems, your Fibonacci series is a classic example. So Fibonacci of n depends on Fibonacci n-1 and Fibonacci n-2, and n-1 again depends on n-2, n-3 and so on. That is not an optimization problem, but for overlapping subproblems, that is an example. So to recap, dynamic programming is a design paradigm used to solve optimization problems where the subproblems are dependent on each other, that is they overlap. So the solution to a problem of size n depends on the solutions to the size n-1, n-2, n-3 and so on and so forth. So it only makes sense that you start from the smallest case and you start computing the solutions from problem size 1, 2, 3, so on and so forth, and you store all these values which you compute, so that when you come to a problem size n question, you can look up these values, you can apply whatever formula has to be applied to them, and you can get the solution to a problem of size n. Therefore, the previously computed solutions are stored and used to compute subsequent solutions. These values are generally stored in a table, a matrix sort of a structure, which is called the DP table. DP stands obviously for dynamic programming. And this process of storing values once computed in a table and then again using those values to recompute some new values is called memoization. Now, the dimensions of the DP table equals number of input parameters is something you will get accustomed to as you solve examples. So I'll not waste too much time on that. The key idea of dynamic programming is optimization problem, overlapping subproblems. Solution to a big problem depends on the solution to the smaller problems, and you store the smaller solutions in something called a DP table and you keep reusing them. So as always, we will start by looking at the blueprint of this design paradigm. So when you looked at divide and conquer, there was almost a pseudocode-ish blueprint where it had if, while, base case, a recursive call, and all of that. For dynamic programming, it is not that not that structured, but we can say there are 2 to 3 core elements which are necessary for an algorithm to classify as a DP algorithm. So those are: 1, simple subproblems, and by simple you mean you break it down into a polynomial number of subproblems. So if there's a problem of size n, you break it down into n minus 1, n minus 2, and so on, or n by 2, n by 4, n by 8, and so on. It should not become exponential. And point number 3, subproblem overlap, we already discussed. And point number 2, optimal substructure, is the single biggest stumbling block in all of dynamic programming. So optimal substructure, in very simple words, is just a formula which will help you solve the problem for size n, depending on the solutions of n minus 1, n minus 2, n minus 3, and so on and so forth. So I told you the solution to a problem of size n depends on the solutions for n minus 1, n minus 2, and so on, right? But what exactly is the dependence? You have all these smaller solutions. What formula or what operation do you perform on them to get the bigger solution? That is what is defined by optimal substructure. It varies from question to question, from example to example, and generally the most challenging part of a dynamic programming question is to figure out the optimal substructure. It's to figure out, using the smaller solutions, how do I frame the big solution. But we are going to look at examples for that anyhow. As of now, the 3 core elements of a DP algorithm are simple subproblems of the same nature. Again, that's not specifically mentioned there, but that holds whenever you're breaking down a problem into subproblems. The subproblems have to be of the same nature. A polynomial number of subproblems, overlapping or dependent subproblems, and there should be something called an optimal substructure, which is a formula using which you can solve a bigger problem, provided you know the solutions to the smaller problems.